Part 2 of Raviv's practice test for test number 2. Looking at this first problem, there's two ways I saw that we can really solve this. The first one being simply voltage nodal analysis, using the same technique that we've been using in the previous problems on this test. So if we want to find VO over here, what we can do is look at this node right here. And remember, the sum of all of the voltages coming out of this node should be equal to 0. So let's do exactly that. Looking at this left branch there, remember that the equation for nodal voltage analysis is going to be high minus low over R. So looking at this, the high is going to be Vx because we are setting this voltage flowing out, and so that means by deduction that whatever is here is going to be higher than what's flowing that way. That's a slanted arrow. Than what's flowing out that way. So whatever's here is going to be higher than the other direction that it's going. So Vx minus 5 volts over resistance 3 plus what is this branch up here? So the high Vx minus the low VO over resistance, which is 3 here as well, plus this last branch, the right one there. And so one of the laws that we are given is that the current always flowing into this is always going to be 0. And so if we want to know the voltage flowing into here, then V is equal to IR, right? And so if the current is always equal to 0, then V is equal to 0 as well. And so we can do plus 0 is equal to 0. And solving for that, we have to find this Vx variable, right? And so another law that we're given is that whatever this voltage here is, it's going to be the same up here. And so we're given here, sorry, let me change colors. We're given here that this is 5 volts flowing into here. And so then we know that also the voltage here is 5 volts. And so now that we know that that's 5, we can do 5 minus 5 over 3, which is equal to 0, plus 5 minus VO over 3 plus 0 is equal to 0. So 5 minus VO over 3 is equal to 0. And solving for that, VO is equal to 5 volts. The easiest way, honestly, just like plug it into MATLAB. Or you can just see that like if we multiply this 3 over here and this 3 over here, then we're left with 5 minus VO equals 0. And then negative VO equals negative 5. And VO is equal to 5. So the second way to solve this is actually ridiculously easy. You're going to laugh when you see this. But if we want to find the voltage over here, voltage is equal to IR, right? And so what's the current flowing in through here? The current is going to be V over R. And so the the voltage here is 5 volts, 5 over resistance, which is 3. 5 divided by 3 is 1.66. And so then we have V equals IR, which is equal to 1.66. And so we know that the current that flows in a series doesn't change. The current is the same. So whatever the current is here, the current is going to be the same going in here. I2. So I1 and I2 are equal. And so if the current we know is 1.66 flowing through here, then we can find the voltage flowing down here by doing voltage equals 1.66 times resistance, which is 3, and 1.66 times 3, and that is going to give us 5 volts. This is actually repeated, so it's like 1.666666. So if you plug that into your calculator, 5 divided by 3 times 3, that'll equal 5 volts. So, okay, yeah, that's using like just concepts from week 1. So that's pretty nice. This second one here, this kind of looks like a mess, but I promise you it's really not. It's very similar to what we just did. And so we want to find the current, right? And so we know that the current here and the current here are going to be the same because these resistors are in series. And so if we want to find the current, I equals V over R, let's find the current here. And so I is equal to 1 volts over resistance, which is 6, and 1 divided by 6 is going to be 0.166, blah 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 blah. It continues. And so we know that this is 1 over 6, right? But if we're trying to solve for this, we know that this current is equal to 1.6, but you know what, look, it's like it's flowing this way, but this arrow is going this way, so they're opposing each other, and that's why we're going to get a negative. For this problem here, we have 2 op amps, one inverted, one non-inverted. Don't let it scare you. We're doing the same thing as we were before. We're trying to solve for VO here, and so I would just simply plug VO into an equation and find VO. And so an equation containing VO is going to be KCL. We can perform KCL nodal voltage equations just as we were doing before. So I would look at a node, this one here, and adding up all the sums, they should equal 0. Alright, and so, looking at this left branch there, remember it's going to be higher minus lower, and if this is V2, remember that this is also V2 just by one of the laws, and so V2 minus Vx, higher minus lower, it's flowing out, so it's going to be lower. We don't know what Vx is yet, and then over resistance, so 1 plus, what is this upper branch there, V2 higher minus lower, which is going to be VO over resistance 1 plus this right branch here, and remember the current always flowing into there is 0, and so therefore the voltage is 0 as well, and set that all equal to 0, and so we're left with V2 minus Vx plus V2 equals 0, and we can simplify that more. Oopsies, I forgot also the VO, plus V2 minus VO equals 0, and so simplifying that more, we have 2 like terms, minus Vx minus VO is equal to 0, and we want to solve for VO, so we can move that to the other side. VO equals 2, V2 minus Vx equal to 0. Whew. Okay, so you can see with this equation here, we need to find Vx, and so let's do that. 2 different op amps I mentioned here. If we look at this big one over here, this one is going to be inverting, and the reason that we haven't just solved for VO using the inverting equation is that honestly, like I Googled it and it's a little bit like long, not complicated, just kind of messy. And so the difference is that, you know, this is inverting, you can tell with this here, and this is non-inverting. You can tell by that there. And the equation for non-inverting is a lot more simple. It's simply going to be Vn, you know, let me write this here. Vn equals R2 over R2 plus R1, times V out. And so, yeah, so as you can see here, this one over here, this is inverting, and that's why we didn't just simply perform that over here, because it's a little bit complicated, so we just solved it using more simple methods. And so, okay, so we have the equation to find Vx here. And so Vx is actually going to be our V out, so it'll look like that. And so Vn, what is Vn? If this is 5, this is also 5, so 5 is equal to R2. R2 is 2 over 2 plus R1, which is 3, times Vx is equal, not equal. Okay, and then solving for that, we can find that Vx is equal to 12.5, if you plug that into Mathway or anything like that. Okay, so now we have our Vx with a simple equation. Vx is equal to 12.5. Come back over here, plug it in. Vo is equal to 2 V2 minus 12.5. Oh, why is that equal to 0? Sorry, that shouldn't be equal to 0. Oops, but otherwise than that, yep, that's how we got there. Okay, so for this one, you know, honestly, this should be the same exact thing that we have been doing before. This is going to be an inverting one here, so remember long equation, so we're just going to do KCL. And to find VO here, we can perform KCL here just like we were doing before. And like the professor has it marked in the answer key, right? If this is 12 volts, then this is also 12 volts here. And so let's mark our little branches. Okay, and so looking at this left branch there, we have 2 higher minus lower, which is 3 over resistance 1, and then plus up here, which is 2 minus VO over resistance 4, plus, remember the voltage going in there is 0, which is equal to 0. And then if we solve for this, 2 minus 3 plus 2 minus VO over 4 equal to 0. And this should give us VO equals negative 2 volts. Okay, so this one we want to find VO and I1. Alright, so you can see by looking at this, this is going to be a non-inverted op-amp because the branch is down here. And the equation, remember, for non-inverting is going to be Vn is equal to R2 over R2 plus R1 times VO. And so let's see how he does the resistors. Yeah, okay, so R2 is over here, R1 is up there. So this is going to be R2, this is R1. Vn is 2 volts, is equal to 11 over 11 plus 10 times VO. If you solve for VO, that will give you 3.81 volts. The current, remember the current flowing both into here and into here is always equal to 0. Superposition. Equation for that is going to be the current is equal to I prime plus I double prime. And the whole concept to these is that you cut off current source, you find the current going through there, you add it back in. And so what the professor does here first, he cuts off this current source there, redrawing it. It looks a little messy, but it's the same thing. All he did was take out this 6 MA. And so solving for the current, let's look at it like that, and current is equal to V over R. Whenever you're going from this to this and going up, remember from the last test that the number is going to be a negative, and if it's looking like that, your number is going to be positive. And so going up through there, I is going to equal a negative. The voltage is 6, and then the resistance, these are in series here, so you can do 6 plus 3, which is 9, and that's how we end up with 2 over 3. Don't forget your units. Okay, double prime. So now what you do is superposition. You add this current source back in, and then you do the exact same thing. Okay, so for double prime, we're going to use the current divider, and remember the current divider is going to be R2 over R1 plus R2 times the source. Okay, so let's say that this is R2, this is R1, and so I double prime is equal to 6 over 9 plus the source, which is 6, because we just added that back in, and so that's how that equals 4. And to find the final solution, we add them both up, so negative 2 over 3 plus 4 milliamps is going to equal 3.33.